Hi folks, here is another tension problem. We have our friend Marvin who has opened a bakery and he wants to advertise his grand opening, so he's ordered a sign. Now the sign is supported by one rope, and that rope goes through a little grommet in the middle of the sign, and the rope, one rope strung through the middle, and it is attached to the roof of his bakery at 2 points, here and here. At each one of those points, the sign makes an angle of 20 degrees below the horizontal. So this is 20 degrees, and this here is 20 degrees. The sign itself weighs 600 newtons, and the question is, what is the tension in the cable? Well, this is a pretty simple problem, because here's what's going on. If we draw our forces, the force of gravity down on the sign is 600 newtons. Tension-wise, we have one tension because we have one cable. We have the tension is going to be the same everywhere in that one cable. So we've got a tension in that cable, and it's kind of pulling in this direction on that sign. So we're looking for tension. And here's the other thing that's wild. Do you remember when I told you the story about the little girl sitting on the swing, and half of her weight is supported by one rope and the other half is supported by the other? If you've got one rope and 2 points of support, each one is going to support approximately half, especially if it's exactly in the center, it will be exactly half the weight. So this tension is kind of the hypotenuse of a triangle. So I'm going to continue drawing this. If there's my tension, this triangle is like that. Part of it is force up, part of it is force sideways, and the force up supported by this support is exactly equal to the force up supported on the other side, and the two sideways forces cancel each other, so the sign doesn't move left or right. Now what I've created there, and I'm just going to redraw it so it's a little prettier, I've got a nice triangle. Here's my tension. Do you remember the mathematical rule of alternate interior angles? If this is 20 degrees, that's 20 degrees. I'm looking for the tension, and I know this side is half the weight, so this is going to be 300 newtons. So all I've got to do is a smidge of trigonometry. If this is the angle I'm working with, here's the hypotenuse. Here's the opposite. If I go SOHCAHTOA, I want the trig function that has hypotenuse and opposite. That's going to be sine. So sine of theta is opposite over hypotenuse. Hypotenuse is what I'm solving for. That's my tension. So that's going to be equal to the opposite divided by the sine of theta. So my opposite is 300 newtons and the sine of 20 degrees. Now if I do the math, what I end up with is 877 newtons. It's actually, the tension in the string is more than the weight of the cable. So let's just take this a little bit further because it's kind of interesting. What if the angle was more shallow? What if instead of a 20-degree angle, what if I had 10-degree angles here and here? Well, let's just do the math. I'm going to take the same equation, 300 newtons, divided by the sine of 10 degrees. Now I've got to punch that in my calculator. So 300 divided by sine of 10, and I get 1728 newtons. I get more than double the tension in the cable. Does this make sense? Yeah, it does make sense, because let's look at it. If I had back to my dead fish analogy, if I just had a fish hanging there, the force of gravity would be equal to the tension in the cable. But if this is now being pulled at some sort of a weird angle, the upward force to make it stay in the same place has to equal the force of gravity, but the tension has to get bigger and bigger and bigger because of the fact there's also a lateral or sideways force. Here's another analogy that might make sense to you. If any of you have ever weighted tables, bless your fuzzy heart if you've ever weighted tables, If you hold right above your elbow, you bend your elbow, and then above your hand, you hold a tray full of food and drink, that's not too bad because your weight is directly over the base of support, which is your elbow. Yeah, I know my person's a little funny looking here. But what happens if the same person would try and hold, here's the elbow joint, hold that same tray way out here? Which one's going to be more easy to do, when the tray is like this above your elbow joint or way out on the end of your arm? This is going to be a lot more difficult just because of the fact that as this straightens out, the angle gets shallower. You actually end up with more and more and more tension is required to hold up that tray. Tension's fun stuff. We'll see you with another problem in a minute.